So this last section of the semester is looking at what the properties of definite integrals can do for us as we're trying to take derivatives of accumulation functions. So here's an example. We have g of x is equal to the integral from x to 9 of sine of t. And we want to figure out g prime of 3. Well, we're used to the fundamental theorem of calculus, which has the constant as the lower limit of integration and the variable as the upper limit of integration. And so this one is sort of backwards from the way we're used to looking at it. So in order to make it look like something we can use the fundamental theorem of calculus on, we need to switch the limits of integration around. Well, we can do that. We can rewrite g of x a little bit. So g of x is equal to negative from 9 to x of sine of t dt. And so now it looks like what we're used to seeing. So now we can use the fundamental theorem of calculus. So g prime would be negative sine of x. And then g prime of 3 would be negative sine of 3. I don't know what that is, so I'm just going to stop. And that's the end. With this, it also, we can ask questions about the behavior of one of these accumulation functions. So this accumulation function is accumulating area between x and 2. So the first question is, what is f of 2? Well, f of 2 would be the integral from 2 to 2. And because of the 0 property for definite integrals, that would have to be 0 because it has a width of 0. F of 0 is the integral from 0 to 2. And that's the order we like it in, so that's okay. And so the integral from 0 to 2 would be a 2 by 2 rectangle, which would be 4, and then a 1 by 2 triangle, which would be 1 times 2 divided by 2, so 1. And so this would be 5. Is f of negative 4 a maximum or a minimum? Well, we know that f prime of 4 might be 0. Let's do a little work on this function before we answer this question. So if I rewrite f of x a little bit, I have negative from 2 to x, and then I'm going to take a derivative of that. So that means that now I'm looking at the y-coordinates are the derivative, but actually the opposite of the y-coordinate tells me the derivative. So f prime is going from positive to negative at x equals 4. So positive to negative, f of 4 would be a maximum. This graph that we have is not a graph of f prime. It's a graph of the opposite of f prime. So every sign that we see here is the opposite of what we would expect. On what interval is f increasing? Well, f is increasing anytime f prime is greater than 0. And f prime would be greater than 0 whenever negative little f is greater than 0. Or another way of thinking about that is where f of x is less than 0. So looks like it would be from negative 6 to negative 4. Number 5, on what interval is f concave up? Well, if I take a second derivative here, the second derivative would be the opposite of the derivative of little f. So it's going to be, so the slope is positive in the graph, which means that the second derivative would be negative. So f double prime of x is going to be greater than 0 when the derivative, first derivative of x is less than 0. So it looks to me like the f is concave up on the interval from 2 to 4 because the graph of little f is downhill on that interval. You also might see functions where your accumulation function actually has variables in both places. We still want to make it look like this. We still want to make it have a constant in a constant to a variable part. So the way we're going to do that is we're going to make up a number. And we can make up any number we want. I usually choose 0. You can choose 50. You can choose whatever number you want. But I'm going to rewrite G a little bit, and I'm going to use the adjacent interval property. Going from the square root of x to x would be the same thing as going from the square root of x to 0. And then going from 0 to x. These two intervals are adjacent to each other. They may have some overlap, but that overlap would be taken care of when we set up this interval. But we can go from the square root of x to 0, and then from 0 to x. Now, we always want the a to be on the bottom, so we're going to fix this. So we're going to make it negative, and then put the 0 on the bottom. Again, the constant doesn't really matter because it's going to go away when we take the derivative. It would matter if we were evaluating this function. Well, actually, it wouldn't because it would cancel out for this particular example, but it would matter if we were if we were trying to evaluate just half of this function. But it doesn't matter when we're taking the derivative because the derivative would be the slope. So then we want to take the derivative of this. So g prime of x would be negative. Now remember the chain rule here. We're going to put square root of x and square it. So that would be x minus 5 times the derivative of x, or the derivative of square root of x, sorry. And then plus, now x squared minus 5. Now if I plug 9 into that, I'm going to leave myself a lot of room, so I'm going to go over here. G prime of 9 would be negative 9 minus 5 would be negative 4 over 2 times the square root of 9 plus 81 minus 5 would be 76. So negative 2/3 plus 76, or 75 1/3. Here are a couple of more examples for you to try. When you've given them a try, you can unpause the video and then see my solutions. So if I'm going to take a derivative of h here, the derivative of, I'm going to have to rewrite this because it's not in the right order. So I'm going to rewrite it as 2x minus plus the negative 0 to x squared. So I'm going to take the derivative of 2x, which would be 2, minus e to the, leave the baby alone, times 2x. So h prime of 2 would be 2 minus e to the 4th times 4. And then G, we have variables in both limits of integration, so we're going to have to rewrite G so that we have numbers on one of them. So I'm going to say, well, this is the same thing as going from x squared to 0 plus from 0 to x. This one looks good, but this one is backwards, so I'm going to rewrite that. Switch the limits of integration, change the sign. And I haven't taken a derivative yet, but now I'm ready to. So I'll take the derivative of g, and I have negative tangent inverse of x squared times 2x, is the chain rule, plus tangent inverse of x. So now g prime of 1 would be negative tangent inverse of 1 times 2 plus tangent inverse of 1. Well, tangent inverse of 1 would be pi over 4, the angle that they have the same sign for, same value for, and so then this would be negative pi over 4 times 2 plus pi over 4. So the final answer would be negative pi over 4. All right. This is kind of an extension of both the previous two lessons where we're applying the properties of integrals, but we're also looking at taking derivatives of these accumulation functions. All right. That is, we're now going to push pause on chapter 6 and return to it after the semester.